Chapter 3 has a very brief review of bonding. It really focuses more on how to name a bond than how bonding itself actually works, but in order to be able to tell the difference, I do still have to do a quick review. If we're looking at pure elements, there is a difference. An atomic element means that your sample has atoms that are unattached to each other. So this is going to be most metals. Okay, so like a copper wire is just a string of copper atoms. They're not really bonded to each other in a traditional sense. Metallic bonding is kind of weird. Whereas a molecular element is like the Brinkelhoff elements, which you may or may not remember from honors chemistry. But these 7 right here, they exist naturally bonded to each other. So, well, bonded to themselves, really. So you'll have, if you have a pure sample of bromine, it's always 2 bromine atoms bonded together. Same thing with iodine and nitrogen, blah, blah, blah. But both of these will count as a pure element. If we're comparing that to an actual bond, there's 2 types. There are what we call molecular compounds, which means that they're made by covalent bonding. And just to remind you of what that is, when nonmetal atoms share valence electrons, that's called covalent. So this example, you can see the carbon had 4 of its own valence electrons, and hydrogens each had 1. And you may or may not remember the octet rule, where most elements are stable if they have 8 valence electrons. In order for that to work, hydrogen actually has to what we call hybridize with carbon. So it will actually blend its orbitals with carbon's orbitals to make a new molecule. And again, we don't need to really get into the nitty-gritty of bonding. It's more important that you just recognize that if C is bonded to H, that's 2 nonmetals. So the rules for how to name CH4 are going to be different from the next type of bonding, which are the ionic compounds. Lithium and fluorine. Lithium has 1 valence electron, which is why it tends to make a +1 charge, and fluorine has 7, so it's going to gain 1. So the ionic bond is the opposite of a covalent bond. This is where one atom actually takes an electron from the other one. So they are not attached to each other after the bonding takes place, but okay, in an ionic crystal, they are attracted to each other because of the positive-negative charges. So the difference between this salt cube and the picture of methane here is that this diagram is supposed to show you that the hydrogen and the carbon are hybridized together. Whereas in an ionic crystal, you have a separate atom of lithium and a separate atom of chlorine. So that's the reason why when they're dissolved in water, the lithium and the chlorine, or fluorine, excuse me, would separate and become attracted to water instead of each other. As a review of ionic bonding, really what you need to remember is to look at the periodic table and crisscross the charges. So lithium always ends up with a +1 charge, fluorine is -1. If the charges are the same, the goal is to get them to cancel out. So if the charges are the same, that means you need 1 atom of each. So you have a formula of LiF. And the way we name it is metals keep their name, and the nonmetals change the end of their name to IDE. So that distinguishes between, if somebody was writing a paper saying lithium fluorine, that's ambiguous because it could mean 2 pure samples of both. The IDE indicates that the 2 go together and that they're bonded. So aluminum is always +3, oxygen's always -2. If we want these 2 numbers to cancel out, then that means we're going to need to have charges of 6. So we're going to need to have 2 + 3 charges and 3 - 2 charges. And the way that we learned it in honors chemistry was to just crisscross the numbers. So you would show that we have 2 aluminums and 3 oxygens in order to get the charges to cancel out. And that gives you aluminum oxide. Again, changing the end of oxygen to IDE. Last one, but like this anyway, +2 - 2. So since these numbers are the same, that means they cancel out. So we are sort of crisscrossing them, but if they're the same number, you don't have to write them. Calcium, it means you just need 1 of each. So this is calcium oxide. Okay, if we have to also review what the polyatomic ions are. So these ions are covalently bonded molecules that have a charge. And so since they have a charge, after they're covalently bonded to each other, they then ionically bond to something else, usually a metal, because most of these are negative charges, so they're going to be attracted to something that would make a positive charge. I will give you a reference sheet with this if I haven't already. If they're bonding, it's the same thing. Okay, we've got sodium always makes a +1, phosphate always makes a -3. So we need to crisscross those numbers. That means we're going to need 3 sodiums to cancel out phosphate. And this is what bothers people because that 4 on the outside makes it look like a 4 came from sodium, but you have to remember that these polyatomics already have a lot of oxygens attached to them. And this is, and the other thing about polyatomic ions, you don't have to change their name. If you remember from honors chemistry, in order to keep them different from a pure nonmetal, we let them keep their name as ATE or ITE, and that's how you can tell the difference between if something is a pure element or if it's a polyatomic ion. So this would be sodium, and then without changing anything, it's phosphate. Okay, so making one more, this is always +2. Okay, if we are transferring the 2 over here, transferring the 1 over here, we're going to have 1 calcium. And then to represent that we have 2 cyanides, we need to put it in parentheses with a 2 on the outside. Okay, if you are going backwards, you pretty much are doing the same thing. Potassium is K. IDE means this is probably regular sulfur, so that's an S. You look up the charge, and then you crisscross the charge. So you have K2S. If we have aluminum nitrate, okay, this is Al. ATE means that's a polyatomic ion, so you need to look it up. It's NO3 with a -1 charge. This is always +3. So we need the 1 here, and we need the 3 to represent that we have 3 nitrates. So the correct way to write it would be with 3 nitrates in parentheses. Okay, so the part that has been skipped so far are the transition metals. They have a little something extra to them because so many of them can make more than 1 charge, and it's only the transition block that has this problem. So for example, both of these, if we were naming them with the regular rules, are iron chloride. There has to be something about them that's different in their name in order for us to know which one has 2 chlorines and which one has 3. Since we've been doing all of this with crisscrossing, what we need to recognize is that 2 came from this iron. Okay, this means that this had a charge of +2, and this iron must have had a charge of +3. And the way we represent that in the name is you would say iron 2, and this one would be iron 3. And then they both end with chloride, because chloride can only make 1 charge, so it does not need Roman numerals. So if you're given a name like copper 2 iodide, this 2 right here just means that the copper has a charge of +2. Okay, iodine is a regular nonmetal, so you just look it up on the periodic table. It's -1. So if we're crisscrossing to make a formula, you have CuI2. And the last example, okay, according to the name, this cobalt has a charge of +3. ATE means we're looking at a polyatomic ion, so SO4 with a -2. We need to take the 3 and put it out here, take the 2, transition it to cobalt, so you end up with 2 cobalts and 3 sulfates.